In this lecture, we're going to talk about electric field and multiple charges. Since the electric field of a single charge is a vector, the electric field of multiple charges may be calculated by adding, point by point, the electric fields due to each charge. The addition is not carried out by just adding the magnitudes of the individual fields. It must be done by adding their vectors. In other words, vector addition. Electric field lines are mathematical abstractions that enable us to visualize the strength of the charge that generates the field and the force that it exerts on other charges that enter the field. There are 4 rules to help us draw these field lines. 1. Electric field lines begin on a positive charge and end on a negative charge. 2. The density of the electric field line's distribution is proportional to the size of the charges. 3. The lines never cross, or else there would be multiple values of electric force at the intersection point. And 4. The lines are continuous. This is the electric field configuration due to two like charges. There is no electric field midway between the two like charges. The individual electric field vectors cancel out. The shape of the field is the same for both positive and negative charges. Only the field direction is different. Notice it exits the positive charges. Notice it enters the negative charges. This is an electric dipole configuration. It consists of two unlike charges. There are no places where the electric field is 0 for a dipole. Again, the shape of the field is the same for both positive and negative charges. Only the direction is different. Notice the field lines exit the positive and enter the negative. Electric dipoles appear over and over again in studies of the atom and molecules. Water molecules are electric dipoles, and this helps explain how microwave ovens cook food, the high surface tension of water, and why water is a universal biological solvent. Later in the course, magnetic dipoles will be discussed, and these have crucial applications. Which of the following represents the electric field map due to a combination of two negative charges? Go ahead and pause the video now. Okay, so let's see if you picked the right answer. You should have chosen E. E shows two like charges. Which of the following represents the electric field map due to a combination of a positive and a negative charge? Go ahead and pause the video if you need to. Okay, hopefully you selected B. B is the correct answer. Net electric fields will now be calculated mathematically and for more than just a pair of charges. So in order to find the net electric field, we have to add up the individual electric fields that are produced by each charged object. Here, notice that the net electric field is equal to the sum of all the electric fields, where N is the total number of fields present at a location. The direction of each electric field determines the sign that you use. Since these are vector quantities, I'm going to go ahead and add a vector sign. Because we're not just adding the magnitudes, we also have to add the direction. The objective is to find the net electric field at the origin for this charged configuration. The first step is to mark the point on the sketch where the electric field is to be calculated. The point is at x equals 0 in this example. Next, we draw the electric fields acting at that point. Next, we calculate E1, E2, and E3, assigning negative values to fields pointing to the left and positive values to fields pointing to the right. Next, we sum the electric fields using this formula. Let's work this problem now with values for the charges. 3 positive charges are located on the x-axis. Q1 is 9.1 microcoulombs and is located at -8 meters. Q2 is 3 microcoulombs located at -2 meters. And Q3 is 2.7 microcoulombs located at 4 meters. Step 1. Mark the point at which the electric field is to be calculated. This is done in red. Next, draw the electric field acting on that point due to the 3 charges. So let's go ahead and take a look at that. Here is what you should have at that point. E1 is going to the right. Let's see why. All of them are positive charges. So the electric field here from Q1 will be going to the right. For Q2, it will be going to the right. For Q3, we're on the opposite side. It will be going to the left, as you can see here. Step 3. Calculate E1, E2, and E3, assigning negative values to fields pointing to the left and positive values to fields pointing to the right. In doing so, we're going to use E equals KQ over R squared. Substituting in the given information, the electric field for Q1 should be 1.3 times 10 to the 3 newtons per coulomb. For E2, it's going to be 6.8 times 10 to the 3 newtons per coulomb. And for Q, this should be a Q3 right here. That should be a 3. Okay, and so for Q3, the electric field strength should be -1.5 times 10 to the 3 newtons per coulomb. Note how a negative value was assigned to E3. This is based on the free body diagram that shows it pointing to the left. Step 4 is to sum all of the electric fields. So let's go ahead and do that. We're going to add up E1 plus E2 plus E3. And that's going to give us a net electric field of 6.6 times 10 to the 3 newtons per coulomb. Again, this is a vector equation. Let me put the vector signs. We do have a direction, right? This is going east. We got to put a plus sign. This is going east, plus. This is going west. That's minus. And so our net answer is going to be plus 6.6 times 10 to the 3 newtons per coulomb. This tells us that the electric field is going east. In the next video, we'll talk about electric fields in 2 dimensions.